This is the second recording for the second question. We will be using Coulomb's law to a two-dimensional situation. In other words, the charges that are given are not sitting in one line, and they, in this particular question, form a square. So the identical spheres, A, B, C, D, with charge of magnitude 5, 10 to the power of -6 Coulomb, situated at the corners of the square, and the side of the square is 25 centimeters long. That's funny, two diagonally opposite charges are positive and the other charges are negative. Calculate the net force acting on each sphere. So let's proceed with this calculation on a new page. Let's do some analysis first. I'll make a drawing. So this one is positive. This one is negative. This one is negative. And this one is positive. So what we will need to do is we need to think about, for example, sphere A separately and evaluate which forces are acting on sphere A. Let me put B, C, and D. So for example, sphere A and sphere C are diagonally across each other, and they will repel because they have a like charge. So if I make a diagonal, I understand that my force will be acting along this diagonal away from sphere A. This is force AC. How about B and D? I'll write them in blue. The A and D are different opposite charges, so they will attract to each other. So let me put vector force AD and vector force AB. And now I understand that three vectors will need to be properly added using vector addition, will need to be calculated proper magnitude and direction. Speaking about the direction, it's pretty obvious and it really doesn't require any additional calculation to state that this is a 45-degree angle, because if the charges are the same, the force is the same between FAD, AB. The two vectors are the same in magnitude, so they'll actually also form a diagonal, and we know that diagonal of a square cuts the square on 45 degrees. So this red one is the result of AB plus AD together. What I don't know, whether the red vector is longer than the pink vector, that I actually don't know. So which way FNet will be pointing, I can't really say. But for now, I'll just state that FNet acting on charge A will be the sum of all three forces, blue AB, blue AD, and pink AC. Now, all charges are the same. I can just use Q for all the three charges. Distance is the same. It's 25 centimeters. What else do I need to observe? I can state, I don't know if you know, but the diagonal of a square in geometric sense is √2 times bigger than the side of the square. So let me just draw a little square here. Does this look like a square? So let's say this is side A, then traditionally diagonal is √2 times larger. Now, if you don't have this knowledge, you can work through using a Pythagorean theorem or whatever, but that is so standard. So basically, to be entirely honest, the magnitude of the red vector is √2 times larger than the magnitude of a blue vector. And I can actually safely state that. So this is √2 times, for example, FAD. So all I need to do is figure out what's FAD. Now as to AC, that we need to calculate separately because the distance that A and C are separated is not the same as AB or AD. So this distance is a diagonal of a square, of a larger square that has the radius of 25. Okay, but surprisingly enough, we can apply the same concept, but that this diagonal, let's just call it D, is also √2 times larger than 25. Can't use 25, have to use, how about I just put R? Hold on a second. Just use R here, like that. So this diagonal, this distance between A and C is √2 times larger than R. I'll just carry on with this knowledge. And now I don't know which way my final vector is pointing, so I'll just say, well, how about I introduce x coordinate along the diagonal pointing this way as I'm choosing to point. And if my result is positive, that's where it's pointing. Okay, so now let's calculate FAD separately. Let's see. According to Coulomb's law, FAD is charge A, charge D, distance between them, which is R. So K, two charges are the same, distance like so. FAC, charge A, charge C, distance K, two charges, and distance √2 R squared. Oh, well, √2 squared is just 1/2. Let me move this a little bit. So what I have, u squared divided by 2r squared. How very interesting. That is FAD, and √2 will be applied for the addition of the two. Just to mention that the sum of the red vectors, sorry, the red vector is along x. Sorry, so when I put instead of AB and AD, I use √2 times k q squared divided by r squared plus FAC. Oh, FAC is pointing in a different direction than my chosen x-axis, so I have to do minus. Minus. What's FAC? It's right here. We have just figured this out. K q squared 2r squared. Well, by estimation, it looks like the first term will be larger than the second because it's √2 and this is 0.5. Okay, so just to make it very clear, this is what we have. And all we need to do now is just to put the numbers in. We have the charge, we have the R, we have the K, and just to calculate all that. Okay, so F net equals, I apologize that I'm not including units of measure, not very professional, but it's okay. So what are the charges? 5, 10 power minus 6. 5, 10 minus 6 squared. 0.25 squared. So punch this all into the calculator step by step or however you want. I'm just going, this is my number from the bracket. 9.20 multiplied by 25 divided by 0.0625. I'm doing step by step. And 10 power 9 and 10 power negative 12. So overall, What do I have? Large 3, 2, 9, 1, 2, 10 power negative 3. So it's just basically 3.3 newtons. Small force, but that's okay. And we already know the direction at 45 degree. And because this turned out to be positive, we made the conclusion that it actually is pointing towards the center. Towards the center. Now, I only calculated the force that is acting on charge A. How about B, C, and D? Will that be different? So the calculation will most likely be the same. And chances are that the total force will also be pointing towards the center. I'll leave that for you to discover.